Hey guys, welcome to 4.1 Antiderivatives and Indefinite Integrals. In this lesson, we're going to be integrating functions and finding their general solutions and particular solutions. So let's go ahead and begin with the example provided here below. If you were given the derivative is equal to 3x squared and asked what function f of x had this derivative, what would you say? So let me rephrase that. Let's say the derivative is 3x squared. If the derivative is 3x squared, what do you call the original function? We call this f of x antiderivative because it is the opposite of the derivative. The derivative is derived from f of x, so f of x is the antiderivative of f prime of x. The symbol, this elongated s gx dx, is called the integral, is the integral of g of x with respect to x. That is what the dx means. It means that you're integrating with respect to x. In other words, if you had another variable there and you're integrating with respect to x, you can't do it yet. Okay? That is going to be part of your Calculus 2 or Calculus 3 class. The term integral is a synonym for antiderivative. So we're going to be interchanging these terms around. Anytime you hear the word antiderivative, antiderivative, I like to think of it as the function that gives you the derivative. The integral, I like to think the integral as the verb. It's the process of taking the antiderivative, of finding the antiderivative. We can get formulas for antiderivatives by reversing the differentiation rules. So we know that in derivatives, anytime that you have the derivative of x to the n, you drop the n, you take one power away from the n, and you get nx to the n. Here's an example. 3x squared, the derivative of 3x squared is 6x. The power becomes a 1, which is just 6x. Now, the integration rule for polynomials of x to the n, like x to the n, are opposite. So notice that instead of multiplying n, we're dividing by n, and instead of decreasing the power of x, we are increasing the power of x. So what I tell my students to do is when you know what n is, plus 1, and whatever that n plus 1 is, put it over the x. So let me give you an example. X squared. Okay, let's say that this is x squared and I want to take the integral of x squared. Its antiderivative is equal to x to the third, and whatever this number is, divided by 3. And then, of course, plus c. Now, why do we do plus c? Because there are an infinite amount of solutions that can give us the antiderivative of x squared. Now, how do you check it? You check it by taking the derivative. Just like the way you guys check your solutions, whenever you find a solution, you plug it into the formula and you check it to see if it's correct. Let me go ahead and take the derivative of x to the third over 3 plus c. What is the derivative of x to the third? It's 3x squared over 3. What is the derivative of plus c? C is a constant, by the way. The derivative of any constant is always going to be 0. 3's cancel. X squared is a derivative. So the integral of x squared is x to the third over 3 plus c. Now here are the rest of the formulas. These are pretty self-explanatory here. The derivative of sine is cosine, so that means that the antiderivative of cosine is sine. How do you check it? You take the derivative of sine and it's cosine. Okay, and I forgot to say plus c here. Take the derivative of sine x is cosine x, the derivative of c is 0, so that's why the antiderivative, all antiderivatives will always have a plus c. If you miss plus c, you pretty much get it wrong. So those are the rest of the integration rules. As you can see that all the derivatives that we have discussed are here, and so are their antiderivative formulas. Some things to know, some key points here is that very much like derivatives, anytime you have a sum of functions, you can take the derivatives of the sum or the difference by taking the derivative of each term. Okay? Now, here you can take the integral of a sum or difference of functions and you can split them apart like this. Let me give you an example. The integral of, let's say it's 3x squared plus x squared over 2 with respect to x. If I want to take the integral of these two terms, I can do it separately. So you can do that with plus or minus. Um, Also, anytime that you have a constant in front of your antiderivative, I'm sorry, in front of your function, you can move the constant to the front. Let me give you an example. For example, let's say I want to take the antiderivative or the integral of 3x squared. I can move the 3 since it's a constant and leave the x squared, and I can integrate x squared and then multiply by 3 last. Some two things you need to know. The integral of a product, you cannot be separated. That's a big no-no. You cannot separate the product using integrals, and same goes for the quotients. Anytime you have a function divided by another function, you cannot take the integral of the top divided by the integral of the top. Very similar to the derivatives. Remember that in derivatives we have product rule. In integrals in quotients we have quotient rules. Now there's no quotient or product rule for integrals, so though that is going to be a much more advanced topic in your next calculus class if you decide to take a calculus 2 course. So let's go ahead and begin with our problems here. So we have the integral of 3x squared minus 5x plus 4. So we're going to integrate 3x squared, or we can use the properties of integrals in the previous page. We can say that this is 3x squared dx minus 5x dx, the integral of 5x dx plus the integral of 4 dx. And then we can integrate each term. Remember that we can only integrate the variables and not the constants. And I'll show you how to integrate constants with this term right here. So integrate the variable, always add a plus 1 to the power, so it's going to be 3x to the third, and then whatever that power is, divided by 3, minus 5x squared over 2, and then plus the antiderivative of a constant is always a constant with an x. That's one thing for you guys to always remember. How is that true? Well, what's the derivative of 4x? The derivative of 4x is 4. So that's how you know that the integral of a constant is always a constant with the x. And then finally, the constant of integration. And then to simplify this, we can of course cancel out the 3's so that my final answer is going to be x cubed minus 5x squared over 2 plus 4x plus c. Now, a quick check. How do we check to see this is true? Let's go ahead and take the derivative of everything here. What's the derivative of x cubed? It's 3x squared. The derivative of 5x squared over 2, well, it's going to be 5x. The 2's will cancel when you bring down the 2, and then plus 4, and you see that you have your derivative there. Okay, so that is one way to check. Let's go ahead and move on to the next problem. The integral of x to the fifth. First, keep the base, add 1 to the base, and whatever the base is, add 1 to the power, and whatever the power is, you divide it by that power, and then plus, of course, c. Next problem, notice that we have an x in the bottom. So what does that mean? That means that we need to move it to the top as an integral. As a negative power, and then we integrate x to the negative third. Same thing, guys. All you got to do is plus 1. What is a negative 3 plus 1? X to the negative 2, whatever that power is, divided by it, and then plus c. Square root of x, very similar. Represent the square root of x as a rational power. You have x to the half. Again, add 1, so you may have to do this on the side, add 1 to the half, and that is 3 halves. And this is where the part gets really tricky here, is that when you're adding fractions, it's 3 halves. So you're going to do x to the 3 halves, and then divided by whatever that power is, plus c. Now, what does a fraction in the bottom mean? It means that you could just move it to the top or to the side as the opposite, x to the 3 halves plus c. Now, here is my trick. My trick is that anytime that I'm dealing with a rational power, if I'm integrating a rational power of x, I'm going to add 1, and then whatever this is, I move it to the front as the opposite. It's just a simple, obvious trick that you can use. It never fails you. This is a repeat of the first problem, so don't skip that problem. What is the integral of sine of x? Let me go ahead and show you guys a trick that I saw a while back. Sine, the derivative of sine is cosine. Derivative of cosine is negative sine. The derivative of negative sine is a negative cosine, and then finally the derivative of negative cosine is a positive sine. You go down for derivatives, you go up for integrals. So find sine. The antiderivative of sine is negative cosine. That is a simple trick. I always tell my students to write it down when they're taking a test or in the AP exam. Okay. And then the antiderivative of secant squared. Now this one is not super obvious, but if you remember your derivatives, there's a function's derivative that is equal to secant squared x. And if this is the derivative, then tangent x is the antiderivative. And then of course plus c. So like I mentioned in the last page, there's not a product rule for integration. So don't do product rule. Instead, use the FOIL and then integrate. So let's go ahead and FOIL. That is going to be 2x squared plus 6x. Negative x and then negative 3. And then combine like terms so that you get the integral of 2x squared plus 5x minus 3, and then with respect to x. Now take the antiderivative of every term. You're going to get 2/3 x to the third plus 5/2 x squared minus 3x, and then of course plus c. In the next problem, like I said, there's no quotient rule, so what do you have to do? You have to divide every term by x squared. So let me go ahead and do that. Let me do it separately, that way you guys know what I'm doing. X to the fifth divided by x squared minus x to the third divided by x squared plus 7 over x squared, and then dx. By the way, if you don't write dx, you may lose credit in the AP exam. What is x to the fifth over x squared? That is x to the third minus 5x plus 7 over x squared is the same thing as 7x to the negative second dx. Now let's take the integral. The integral of x to the third becomes x to the fourth, and then divided by 4. The integral of negative 5x is negative 5x and then squared, and then divided by 2. Finally, the antiderivative of 7x to the negative second plus 1. Put a plus 1 on that power. A negative 2 plus 1 is a 7x to the negative 1 divided by negative 1 plus c. So all these solutions that we just derived, all these answers that were plus c, are called general solutions. So let me go ahead and read from what this text says here. A differential equation is an equation containing a derivative. Okay, it can be any derivative. It can be a first, second derivative, and so on. To solve a differential equation means to integrate and find f of x or y. When you first integrate, your answer with the plus c is called a general solution. Now, what does that mean? A general solution is a solution where we have a constant, where the constant can be any number, and the way to solve for c, we would need a point. So let me go ahead and continue reading. Then you use your initial condition. to find c so that you can substitute it into the general solution to find a particular solution. Okay, so example number one, we're going to go ahead and solve the differential equation. So we want to find a particular solution. A particular solution is a solution that gives us a answer plus c, but where c is actually a number and we have to solve for it. So let me go ahead and let's go ahead and write this f prime in a different way. Always write the f prime or the derivative in terms of this notation here. dy over dx equals 6x squared. Now, one thing that we haven't done in class is that we haven't separated these two notations here, dy over dx. We can actually multiply dx to both sides so that we get dy is equal to 6x squared dx. And then we can take the integral of both sides. We can take the antiderivative of both sides. The antiderivative of an imaginary 1 dy is just a y. The antiderivative of a 6x squared is 6x to the third divided by 3 plus c, which is the same thing as 2x cubed plus c. So y is equal to 2x cubed plus c is called a general solution. It's general because c is not defined yet. So there could be many answers for c. We're going to go ahead and use the initial condition here. F of 1 equals -3 is the same thing as 1 comma -3. Let's go ahead and substitute these x and y values and solve for c. -3 is equal to 2 times 1 cubed plus c. -3 is equal to 2 plus c. C is equal to -5. And our general solution is y is equal to 2x cubed minus 5. So c can be negative. So just because it's plus c doesn't mean that c is actually a negative number. In this case, it's negative, so it's going to be a minus whatever that number is. Last problem to finish it off. Solve the differential equation f double prime of x is equal to cosine, given that the initial condition for the derivative is 0, 3. This is for the derivative. And then the initial condition for the function is 0, -2. Now, here's the tricky part. We have a second derivative. No matter, we're still going to go ahead and solve for y. So that means we have to repeat what we did in the previous problem twice. So how do we write f double prime in the other notation? It's d2y over dx2 cosine x. So let's go ahead and multiply dx2 to both sides so that we get d2y is equal to cosine x dx2. All right, so we're integrating with respect to x. The antiderivative of anything with respect to y that has a number in the front is just going to be the number y, the number and y. So here's an imaginary 1, so this becomes y. Okay, now this is really the y prime because we're integrating a second derivative, which means we should get out a first derivative. And then the antiderivative of cosine x, we already know, is sine of x, and then of course the constant of integration. We're going to go ahead and use our initial condition for the derivative to solve this c. So 0, 3, 0 is the x, 3 is the y, so it's 3 is equal to sine of 0 plus c, and it's obvious that sine of 0 is 0, so c is 3. Now, because we're going to do this again, I'm going to call this c1. Okay, I don't want you guys to confuse your c's. This is my first c because we're going to have to do this to get our regular y. So y is equal to sine of x plus 3. This is my derivative. This is my particular solution of the first general solution right here. Now let's repeat this process again. dy dx is equal to sine x plus 3 Let's go ahead and separate. dy is equal to sine x plus 3 in parentheses dx. Now integrate both sides so that the integral of a dy becomes a y. The integral of a sine we know is a negative cosine. The integral of a 3 becomes just simply 3x, and of course plus c. Now we're going to use the initial condition for the function x, y, and we're going to go ahead and plug it in. So it's going to be negative 2 is equal to negative cosine of 0 plus 3 times 0 plus c. 3 times 0 goes away. Cosine of 0 is a positive 1, which makes this a negative 1 because of the negative, plus c. And if I add 1 to both sides, I get c is equal to a negative 1. So my general solution for y becomes a particular solution now that I have c solved. So it's y is equal to negative cosine x plus 3x minus 1, and this is called my particular solution. It is not general. It is an exact solution with all variables and parameters defined here. So this concludes the lesson for the antiderivatives, and I'll see you guys in the next video.